One of the wonderful things about reading the work of William Gilbert and then of Benjamin Franklin is that you get a good sense of the kind of detailed work that needs to be carried out in order to understand how nature works. It's very different than reading a contemporary textbook on physics where you're memorizing formulas, plugging in numbers, and learning how to solve problems. Here, by reading the work of Benjamin Franklin, you can understand the kind of trials and difficulties that he went through in order to establish some of the physical principles that he's working on. Today, we'll be looking at letter 3, which was written in 1747 to Mr. Collinson. This is collected in Benjamin Franklin's Experiments and Observations in Electricity, and this is recorded in A Student's Guide to the Great Physics Texts, Chapter 4 of Volume 3. So let's begin by talking about his work with a Mueschenbroeck bottle. So, in letter 3, which is on page 44 of A Student's Guide, Franklin discusses his work with what is now called a Mueschenbroeck bottle. This is also called a Leyden jar because Professor Mueschenbroeck studied this in the Leyden laboratories. And as an aside, the Leyden laboratories played a very pivotal role in much of modern physics. That is where Kamerlingh Onnes discovered superconductivity in the early 1900s, as well as the early work on liquefaction of gases, liquid helium, and superfluidity. So this is a very storied lab, but what we're interested here is the early work on electricity that was carried out by Mueschenbroeck. So what is a Mueschenbroeck bottle or a Leyden jar? Well, it's an early version of what we would today call a capacitor. So let me make a sketch of what a Mueschenbroeck bottle looks like. Here you have a metal ball attached to a thin metal wire. This passes through a cork, and the cork is inserted into a bottle. That's why, after all, it is called a Mueschenbroeck bottle. I'll make the bottle in green. This is a cross-sectional drawing. So this is the glass jar or bottle. This is a metal ball and a wire sticking down through the cork, which is an insulating material. And the idea is that if one were to take a rod of glass, let's say, a glass rod, and rub it with silk or some other kind of, or leather, one can make it charge positively. As Benjamin Franklin would say, it accumulates the electrical fire. And then by touching this metal ball with the glass rod, this can be made to be charged positively. This glass jar can then store the charge, and one can do experiments on this. By the way, what Benjamin Franklin is going to argue is that when this becomes positive and this wire sticking down into it becomes positive, the exterior of the jar becomes negatively charged. I should also add at this point that in the version that Benjamin Franklin is working with, there is water in the jar. And he's going to be interested in where exactly this charge is being stored. It would be worthwhile at this point to mention that there are later versions of this jar that Benjamin Franklin studies. So let me import a picture that illustrates a later image of this jar. This is a later version of the jar. How this differs is that one has, once again, this metal rod passing down through it. There's a chain that's hanging down onto the inside, and the chain is in contact with a metal foil that coats the inside of the glass. There's also a metal foil coating outside of the glass, and also there is no water. So in later versions, there is metal foil coating the inside and outside of the glass, and there is no water. And maybe it'd be worthwhile for me to mention right away that where eventually this leads to is the modern day capacitor, which consists of a metal foil attached to a metal wire with a glass or mylar or some other insulating material, and then another metal foil like this. So it's kind of a sandwich with it's a sandwich with metal foil on the outsides and some mylar or other insulating material on the inside. So this is the modern day capacitor right here. We'll come back to that later. Now, what are the kinds of topics that Benjamin Franklin is going to address in this in this letter? Well, there are several questions that he is interested in answering. the first question is, how can the Mueschenbroeck bottle be charged? We already mentioned here, by electrifying a glass rod and touching it, that's one way that it can be charged. A second question one might ask is, where does it store its electrification? The general question is in the bottle, but more specifically, is the electrification stored on this metal wire? Is it stored in the water? Is it stored in the air that's above the water? Is it stored in the glass? Is it stored, if in the glass, within the glass or on the surface of the glass? These are the kinds of questions that Benjamin Franklin is interested in answering. Number 3 is, how can the jar be de-electrified? We would say today discharged. He doesn't use that kind of language of charge. Okay. And here's another question that's very interesting, is how is it that a jar like this can remain in a static state so far out of equilibrium? Or in other words, how can an electrified jar remain charged, remain electrified, since it is out of equilibrium? What do we mean by this? Well, you might recall the idea that he has is that when you have some substance that's electrified, what that means is, so when you rub glass with silk, you rub them together, the glass acquires some electrical fire and the silk loses electrical fire. So one has an excess or positive charge, an excess of electrical fire. The other has a deficit of electrical fire. We call that negatively charged. Those two objects are then out of equilibrium. When we charge up a jar like this, we have the interior of it that's positively charged. It has an excess of electrical fire. The outside of it is negatively electrically charged, so it is a deficit of electrical fire. These things naturally want to reestablish equilibrium. So how is it that this thing stays so far out of equilibrium for so long? And to sharpen the point, Benjamin Franklin notes that if you were to take a jar and you were to put a cork in it, but somehow you were to make it so on one half of the jar it's a vacuum, and on the other half of the jar you have air, clearly this is out of equilibrium. The air would quickly diffuse into the vacuum and it would fill the space up. So when you have a system that's out of equilibrium, it will naturally attempt to reestablish equilibrium. But this doesn't seem like what happens with a jar like this. So in trying to answer the question of where the electrification is stored, he's going to try to address this question of how it can be remaining so far out of equilibrium. Okay. Let's go on to one of the next pages. So the first couple of pages in this, page 44 and 45, what Franklin does is provide a summary of his experiments. Let's come back to this later, and let's just talk about some of the experiments he carries out. So let's first talk about experiment 1, and we'll spend a couple of minutes on this, and then we'll probably stop and talk about experiments 2 and so on later. So what does he say? He says, suppose we were to take one of these Leyden jars or Mueschenbroeck bottles, and you were to place it on a wax block. So here is the Mueschenbroeck bottle, and you were to place it, like he says, upon a wax block like this, and you were to electrify it. Okay, so when you electrify it, it makes it so that, let's suppose that this is positively charged. And then suppose one were to take a small ball and bring it near it, a cork ball or a pith ball, as he says, which is suspended from a thin silk fiber. If this is an initially uncharged object and you bring it near it, you might think that because this is positively charged and this is neutral, that it would not be attracted or repelled. But what he notices is that as you bring it close to it, this neutral ball is actually attracted toward this positive charge. And then he says, once it touches it, then suddenly it's repelled. So a neutral or an uncharged object, a non-electrified object, non-electrified ball, is first of all attracted to, let me move this to the other side, to the wire, that charged wire. Secondly, it touches it. And third, it is repelled from it. So it hangs, it will swing toward it, touch it, and then suddenly swing away from it. Okay? So what's happening there? And once it's repelled from it, then he says if you take this string and you move it downward, you move your hand downward. So this is first attracted, that's point 1. Then it's repelled, that's point 2. And then if you move your hand downward, then you notice that this ball is attracted toward the bottom of it. So where it's repelled from the top, it's attracted to the bottom after having been touched. So I just want to lay out that observation. First of all, this is experiment number 1, and we'll talk about this when we get together next time.